In this lesson, we're going to be going through the steps of RSA key generation. So remember, we need two keys. We need a public key and we need a private key. The public key is what's used to encrypt the data. The private key is what's used to decrypt the data. So the heart of asymmetric encryption lies in finding two mathematically linked values, which can serve again as our public and private keys. So as such, the bulk of the work lies in the generation of such keys. So we have 5 steps that we need to go through when doing this. The first thing that we need to do is we need to select two primes, P and Q, and they have to be distinct. Now, for our example, we're going to keep these relatively small, but in reality, they're not going to be relatively small. So that's the first step. The second step is we want to calculate the product N, which is equal to P times Q. Then our third step is to calculate K. So K is equal to the product of P minus 1 times Q minus 1, which, as I said, this is not going to be prime. So what we want to do now is we want to select a private key D that has the following property, that DK is congruent to 1, the GCD between D and K is equal to 1. Now, once we have this met, then we know mod K that D has a multiplicative inverse. So there will exist a public key E such that DE is congruent to 1 mod K. So the big work is finding the private key, then the public key comes afterwards. But this is it. Those are the 5 steps to generate our two keys. So our public key would be E and N, because again, we're doing all the calculations mod N. And then our private key would be D, and again, N as well. So message encryption, so using the keys we generated above, we run through the encryption process. So recall that with asymmetric encryption, we are encrypting with the public key and decrypting with the private key. So the formula to encrypt with RSA is, we'll take the ciphertext, which we'll call it just C, is equal to our message M raised to the power of E mod N. So again, when we're given something to be encrypted, we give the public key, which is E and N. So whatever our message is, we raise it to the power E mod N. Then we have the encrypted message, which can be sent back. Now the formula to decrypt with RSA is to get that original message back, this is equal to that ciphertext, that encrypted message, C raised to the power of D mod N. So what this is doing is this taking the original message, raising it to the power ED, and getting back the original message exactly as the last theorem stated. So now the question is, well, how do we encrypt a message? How do we take something and turn it into that M that we're looking for? Well, what we're going to do in this example is just keep something very, very simple. We're just going to encrypt spaces and letters. So we're going to assign a 2-digit number to this. So the message to be sent needs to be first converted to numerical form by replacing each letter or space by a 2-digit number. So the space were represented by 00. A being the first letter of the alphabet gets 01, B 02, and if we continue this all the way down the alphabet and 26 items in the alphabet, or letters in the alphabet, Y is going to be equal to 25, Z is going to be equal to 26. Okay, so now that we have this idea, let's go through an example. We want to encode the following message: I love algebra. So we don't want anyone else to know that we love algebra. So what we're going to do is we are going to break this down into sub-messages, and we'll speak about why we have to do that. We're going to encrypt that, and then we can send the message out to whoever we want, but the only people that can decrypt it is in fact us, because we will have the private key for this. All right, so let's go to the workspace. So this is the exercise. And what we're looking to do is encode I love algebra. So the first thing is I want to start building my messages. Now what I'm going to do is I'm going to put 2 letters, or a letter and a space, or space and a letter together. So I'm going to break this down into I, and then I'm going to represent a space by a pound. then love is going to be broken into LO and VE. Space, so again, pound, and then algebra. So space A, LG, EB, RA. So now, from before, I'm assigning a number, a 2-digit number, to each one of the spaces and each one of the letters. So I had a 2-digit value of 09, space is 00. So I space is 900, or 0900. LO, L is 12, O is 15, so this message is 1215. VE is 2205. Space again 00, A is 01. That's not going to be a difficult one to encrypt. LG 1207, EB 0502, and last but not least RA, which is 1801. Now the question is, why did I break it down into this form? So the next part is I have to first pick out a P and a Q. Well, we're given a P and a Q in this case. So our P is equal to 47. Our Q is equal to 59. So that means N is equal to the product of this, which is 2,773. So this is the reason why I've broken messages down like this. So the largest message I could have when I'm only using 2 letters or a letter in a space or some combination of that would be ZZ, which would be 2626 or 2,626. Now what I want to do, since all this is being done mod n, I want to make sure that each one of my messages is unique. So I don't want any message being larger than what my n is. I don't want it larger than 2,773, because if it is, then it is possible for me to have 2 different messages meaning 2 different things. I don't want that. So we need to make sure that each message, or the length, len, of the message, which we'll say is m, is less than n. And in this case, if we look through all of these, the largest message we have is 2,205. Well, that's less than the 2,773. So all our messages are safe. They're all going to, in fact, be unique. All right, let's get some more space here. All right, so going through the process of this, again, typically we would have to find a P, we would have to find a Q. So this would be the steps to generate keys. So we have a P, we have a Q, so we have step 1 down. Step 2 is calculating our N. Step 3 is K, which again is equal to P minus 1, Q minus 1, or the product of the two, so that is 46 times 58, which works out to 2,668. Obviously, this is an even number, so it is not prime. So what we need to do now for step 4 is we need to pick a D such that the GCD of D and K is 1. So in this case, we're going to let D be 157. We're making that claim that 157 and 2,668 are in fact have a GCD of 1. Now, we can test whether or not this is true using the Euclidean algorithm. So if we do a check here, we're looking to solve for 157, or the GCD of 157 and 2,668. This is going to be equal to, well, let's go through the process. So the first thing that we're going to do is we are going to break down 2,668 into a product of some multiples of 157. So how many times does 157 go into 2,668? Well, it goes 16 times, and I'm going to be left with a remainder of 156. Now my algorithm states if I have a remainder of 0, I stop. In this case, I don't, so I repeat the process. Now what I'm doing for the next step is my quotient here, this 157, now becomes my left-hand side. So I'm going to break this apart down. My remainder, that 156, is now going to be the quotient here. So how many times does 156 go into 157? Well, it goes once, and I'm left with a remainder of 1. Yeah, that's not 0, so I continue on. So 156 moves to the left-hand side. That's my quotient. My quotient now this time around is going to be 1. How many times does 1 go into 156? It goes 156 times with a remainder of 0. Thus, we stop. And that's our GCD. So it's equal to 1. All right, so that's step 4 complete. Step 5. Now that we've chosen that specific D such that D and K have a GCD of 1, we know that the following is true. We know there exists a DE that is congruent to 1 mod K. And to find that E, well, we can do a couple of tricks to be able to do that, but I'll just give it to you here. This is going to be E is equal to 17 mod K. Now, how did I find that? Well, a little bit of work. But what I can do here is I can set it up in the following way. Again, I know what D is. D is 157 multiplied by some E, and this is going to be equal to 1 mod K. Well, instead of writing it as 1 mod K, this could be 1 plus any multiple of K that we want. This would also be true because multiples of K are really in fact just 0. So it's the same as 1 plus 0. So let's do that. Let's take 157 times E, and I'm going to change 1, and I'm going to take 1 and add to it K, which is 2,668. Again, mod K. So I have 157 E is equal to 2,669 mod K. Now notice that 157 didn't divide 1 the first time around, but 157 divides this new version of 1. Again, looks slightly different, but means exactly the same thing, mod K, or mod 2,668. So if I divide both sides by 157, I get E is equal to 17 mod K. And sometimes you'll be able to solve in these sort of ways where you can add on multiples of K and be able to divide through and finally get to what E is. Sometimes it's not always going to be that easy. But there we go. So step 5 is done. So that means our public key is E, which is 17, and 2,000. Whoops, sorry, not 2,000. It's N. 2,000 is right. It's 2,773. And our private key is D, that 157, and 2,773. So if I want to encrypt a message, I use the public key. To decrypt that message, I use my private key. So what we're going to do now is we're going to take each of these messages. So we'll call this M sub 1, M sub 2, M sub 3, 4, 5, 6, and last but not least 7. So what I want to do is I want to create a C1, which is going to be equal to, well, let's write this a little better because this kind of looks like an E. C1, which is going to be equal to M sub 1. And now using the public key, this is going to be raised to the power of E mod N. All right, so our C1, our original message, this is I space. This is 0900 raised to the power E, which is 17. This is equal to 1,510, again, mod 2,773. C2, our message was LO, which was 1215. So raise that to the power 17. This gives us 0417 mod 2,773. So that's our second encrypted message. Third one, this is VE, which was 2205. Again, raise that to the power 17. We have 1524 mod N. C4, this is our space A, so 0001. Raise that to the power 17. Well, that's 0001. No work has to be done there. That's kind of nice. Again, mod 2,773. C5. This is our LG, so 1207 raised to the power 17 gives us 723 or 0723 mod. I'm just going to write mod N from now on. C6. So this is our EB. So 0502 to the 17. 1,804 mod N. And last but not least, C7. This is our RA, which is 1801 power 17, which is 2003 mod N. So there we go. We were able to encrypt the I love algebra into 7 crypted messages. So that's our C1 through C7. I'll leave this as an exercise for you folks. Decrypt these, make sure we get the right ones back. So in order to decrypt this, we use the private key. So again, taking each one of these coded messages, raising it to the power 157, and then modding by 2,773, which is our N. All right, that's it for our first application. We'll see you back when next time we're jumping into groups and subgroups. So it's a brief introduction to that. We'll see you then.